Okay, good afternoon. Hope everybody's okay. Just wanted to ask, we only had one entry in this video competition, and that was from Mark. Is Mark here? Huh? He's hiding up? Not? Oh. Would you like to see his video, though? So, this is more with the idea that we don't, hang on, that's not it. Video one, okay. See if this works.
Height of 1.24 metres. I say 0.42 seconds to the ground. F squared, I squared, square over x. I'm going to go with 4.9 metres a second.
So I guess this is Mark showing his awesome powers of mental arithmetic. So we're not expecting you to do anything really complicated, but it's just nice team building exercise. If you could put up some videos, I'll put up another competition for the end of next week, I guess. Do see what you can do. Maybe try to speak a little clearer. I wasn't quite sure what he was saying, but that didn't really matter. It was still something to do with physics. And so today we're doing more to do with physics, and today we're going to talk about momentum and impulse. So this is going to allow us to simplify some of the calculations we might want to do. Really, it's not giving us extra information, but it's many times in physics you want to have a different way of looking at things so that you can figure out how to do a problem without too much difficulty. So we'll talk about impulse. Impulse is sort of the force acting on something for a certain amount of time. And we're going to relate that to a quantity called momentum, which is a very important quantity in physics, and it's a quantity that is generally conserved. And things that are conserved are really useful because they often give you ways of doing calculations without doing so much work. And in physics, we don't like to do too much work. Might not seem that when you're doing the course, but the idea is to do things as simply as possible. So the impulse, according to these pictures, the impulse is the golf club hitting the ball, the soccer player hitting the ball with his head, or these billiard balls, pool balls hitting each other. Now, when we've talked quite a lot about Newton's third law, that if you have objects pushing on each other, the force of one on the other is equal and opposite. So here in the picture, the block B is exerting a force FB on A. Block A is exerting a force in the opposite direction, but the same magnitude on B. That's the FA. And when we have a collision, it's not actually instantaneous. When the ball looks like it's bouncing fairly instantaneously, but actually if you slow it down, you get these scary sort of pictures showing that the ball's actually in contact with the table or with the player's head for a short amount of time. And we can represent this as a graph of force against time. So time is going like that, and before the ball hits, there's no force, and then the force will get bigger, and after a while it will get smaller after the collision. Now, of course, if you have to do the calculation with these complicated curves, that would be really annoying. So generally, we will make simplifications. We'll say, oh, well, maybe that's approximately looks a bit like a triangle, or even maybe it looks, maybe you want some sort of average, and it looks there's some kind of average over a certain amount of time. But anyway, I forgot to put in the scale. It was the force in that direction. So keep in mind that what we're doing is just an approximation, but the idea is to get some idea of how big things are. So the effect that the force has is not just the highest point that it gets to, not just the maximum force. The effect of the overall effect of the force is actually the area under the curve, and that area is called the impulse. That kind of makes sense, you know. If I just hit the ball with for a short time, it doesn't do much. If I applied the same force for a longer time, the ball would accelerate much more. So let's think about this problem for a second. So we have two 1 kilogram cue balls. Sounds pretty heavy for a ball. Anyway, we exert these forces, either this force, I think we've lost the scale over here, this amount of force, 100 newtons for 2 milliseconds, or I think this was supposed to be about a fifth of that, about 20 newtons? I'm not sure. Actually, it's actually quite difficult to answer this question since we don't actually know what the scale is. So, which ball has the final speed? So, what this was supposed to show was that both balls would have the same final speed because the total, the integral, the sum, the area under the curve, the force times the time was the same, except you couldn't really tell that from the picture, so I'm sorry about the rather useless picture we had there. Now often instead of just, if we want to just think about the area, it's often useful to think about the average force, and that would be this rectangle here. That has about the same area as the blue, as is under the blue curve. Now, there's some interesting things about the units here. You've got newtons. Force is given in newtons, time is given in seconds. So our impulse, force times time, is newtons times seconds. But remember, we have that equation: force equals mass times acceleration. So newtons, you can also write newtons as kilograms meters per second squared. So force times time is also has the units kilograms meters divided by seconds squared times seconds. So one of those seconds cancels out. impulse kilograms meters per second, or newtons times seconds. Okay. So if we have a ball, we don't want to have to do this complicated curve, so maybe we just approximate it as a triangle, and we say that that's, in that case, 8. We're just making this up, really, but it's roughly right for certain things. This is 8 milliseconds, so that's 8 times 10 to the minus 3 seconds, or 0.008 seconds. So in these diagrams, do pay attention to the units. If that was 8 seconds, that would be very different from it being 8 1,000ths of a second. So there's maybe a certain force there, 300 newtons in the case of this little explanation. So we can take that triangle and figure out what the area is. And the area of a triangle is half the height times the base. So you just multiply the 300 by 8 and divide by 2, but you need to also divide by 1,000. So it's a half of 300 newtons times 0.008 seconds, 1.2 newton seconds, or 1.2 kilograms meters per second. And so then if we want to know the average, we're spreading that out equally instead of as a triangle, and it shouldn't be any surprise that the average is 150 newtons, because you expect that to be half of the height. If you take those little triangles out, those will fill in the holes there. So what we're going to do now is to relate that impulse and use Newton's laws and figure out how to relate that to the idea of momentum. So we had the average acceleration was the average force divided by the mass, and average, and that's the final velocity minus the initial velocity divided by the mass, divided by the mass, divided by the time, right? So it's the acceleration is the change in velocity divided by the change in time. And then, so these two are actually the same. So the average force divided by the mass is equal to the change in velocity, Vf minus Vi, divided by the change in time. And so what we're going to do is to rearrange this equation a little bit. We're going to multiply both sides by delta t. So we have F average delta t, and multiply both sides by m, so that it's m Vf minus m mvi. And then we're going to call that the momentum. So that's the final momentum minus the initial momentum. So in some ways we're not this momentum is something that if we know the mass and we know the velocity, we can work out what the momentum is, but it's very useful to have that concept. Momentum is mass times velocity, so that's kilograms meters per second. And of course, because the velocity is a vector, the momentum is also a vector. So it's a vector in the same direction as the velocity, but of course there's a relationship. It's related by m. So something that's going very fast tends to have a higher momentum. Something that's heavy tends to have a higher momentum. And there's just some numbers, just for fun: raindrops, bullets, baseballs, running person. That's 3. It's not that fast to run, is it? But anyway, it's a running person or a car driving down the highway, which can have quite a lot of momentum. And so the momentum is related to the impulse, because we remember the impulse was what was our definition of the impulse? We had this back here, where it was newtons times seconds. You know, it's the amount of you apply a force for a certain number of seconds that will cause acceleration, and so it will cause a change in momentum. So J is the change in momentum. And we can do this with vectors, the x components and the y components. So these are just examples of putting a golf ball or hitting a football, and we're changing the momentum of the ball in both cases. So here's a little example. So here we have the ball going towards the wall, and the mass was 0.25 kg. This velocity was plus 1.3 meters per second, and then bounces off and it comes back. The velocity is a little bit smaller. That's normal, isn't it? Vxf equals minus 1.1 meters per second. That's kind of normal. If I bounce a ball, it usually doesn't bounce as high as where I drop it. It bounces, it loses some of that, it loses some energy in the bounce. So what we want to do now is think about how do we work out this change in momentum, and how do we work out therefore the impulse. And we're setting up a coordinate system with x in that direction. So that means that before the collision the momentum was positive, and after the collision the momentum is negative, because Vx is negative. So that's a whole lot of words. So if you just multiply these things out, before the collision you've got 0.5 times 1.3. The momentum is 0.325 kg/ms. And then after the collision, the momentum, because we've got a negative quantity there, you've got 0.25 plus 0.25 times minus 1.1, it's minus 0.275 kilograms meters per second. Now, this is the point that you have to be careful. You want to know the change in momentum, and that's the final momentum minus the initial momentum. And so it's really important to notice what the signs are. So this is negative, this minus 0.275, that's negative. And then there's a negative sign there, but this other one is positive, minus 0.325. And so that sum of those is minus 0.6 kgms. And it's very easy to get this wrong, you know, to say, oh, well, before it was 0.32, now it's 0.275, so the difference is 0.32 minus 0.27, and that's not right, is it? Because you've actually changed the direction. You've gone from one direction to another direction. You've got to put in the right signs. And let's think about why the sign is negative, because the impulse or the force is going in that negative x direction. This is something at the bottom. It's something useful there. If you can make if you're going to have a collision, if it takes a longer time, then the force of the impact will be less. So that's why a modern car, you know, if you hopefully won't crash into something, but if you do crash into something, the front of the car is built so that it collapses. So that you're slowing down for a longer time. If you make the car completely rigid, it's not actually as safe because it's going to stop immediately. And then that force will be transmitted to the driver, which will be bad. Okay, so I think the message here is to be like a hedgehog. Because the hedgehog has those spikes, if it lands on the ground, the spikes take a while to compress, and the hedgehog doesn't get hurt. So here's what was that one? It's a puck. Okay. So this example problem, I mean, the text doesn't really, you'll find, doesn't really match the picture. We have this 0.5 kilogram hockey puck, and so we're saying it's sliding to the right. I mean, it's sliding to the left in that picture, but never mind. It's going at 10 meters per second. And then it's hit by a hockey stick. This was m equals 0.5 kg. Then you hit it with the hockey stick. It's doing that. It's 10, 30. This is in milliseconds. Time in milliseconds. This maximum is, say, 50 newtons. And now, which direction do you think that is? I guess if this is going to be positive, it's going to be in the positive x direction. So let's say that force is in that. Force is being applied in that direction. It doesn't really matter. This is just an example. But you know, when you're reading these things, you sometimes need to think a little bit. You know, what did the person writing this actually mean? So what's the final speed going to be? So you think about maybe we could make this into a triangle. And so the impulse or the change in momentum is going to be the height times 30 minus 10 is 20. Times 10 to the minus 3. So that was in newtons, that was in seconds. So that's, and then we need to divide it by 2 because it's a triangle. Okay. So that was the area. So if I work that out, I get 50 times 0.02 divided by 2. I can cancel out the 2's and I get 0.5 kg meters per second for the impulse or the change in momentum. So since delta P is m times delta V will have to be delta P divided by m, which is 0.5 kg meters per second divided by the mass, which was 0.5 kg. So those are going to cancel out, and we're going to get 1 meter per second. So according to my calculation, the change in the x component of the velocity is only 1 meter per second, and then I'll have to add that. So the final, so Vf is Vi plus 1, 10 plus 1 equals 11 meters per second. So that seems like a pretty pathetic attempt at hitting the hockey puck, and not nearly as spectacular as this picture on the video. Right, so we have a bit of a rest here. So what's this question? A light plastic cart and a heavy steel cart are being pushed with the same force for 1 second. So after we remove the force, is the momentum of the light cart greater than the heavy cart, equal to, less than, or I don't know? So what have we got? Greater than, equal to. It's all looking fairly, looking very even here. Except there is no E, so that can't be right. Okay. So you need to think about what does this mean? If you have the same force pushing for the same amount of time, does it actually matter how heavy the cart is? You know, this is the force. The impulse is force times time. The heavier cart will be going slower and the lighter cart will be going faster, but the actual change in momentum is the same for both of them. So here's a summary of momentum and impulse, what we've done so far. And not today, but later on we'll talk about total momentum, because that can be very important when we talk about collisions. So if we had, if we have two balls and they collide with each other, what this is saying is the total momentum of the system is the sum of the momentum of the individual particles. And so if you had these two balls colliding with each other and there were no other forces, they can both change momentum, but the total momentum is going to stay the same, and that's going to be very important later on. So let's talk about how to solve these problems. We've already kind of done this. I didn't do it very particularly well. But when we drew this picture of the ball bouncing off the wall, we've got a before picture and an after picture. So that's a useful way of getting your thoughts together. This is what was happening before the collision, or before bouncing off the wall. This is what was happening after bouncing off the wall. And as with all our other cases, you want to figure out what's the coordinate system, especially if it's not just in a straight line. You need to figure out, label which is x and y so you don't get lost, and write down the information you know and the information that you want to know, and then you can start thinking about how to put it all together. So we keep repeating this, but this is, as I said, I often come and try to help students, and they're just sort of sitting there trying to do it completely in their head, which I think is quite hard. And it's not something I can really do very well. Now this example is pretty similar to the example that we just did for the hockey puck. So I'll go through this, but I don't want to go through it terribly carefully because we've already just done a similar problem. So this is saying the baseball is thrown 20 meters per second and it's hit straight back at 40 meters per second. So in this case, rather than bouncing off the wall, it's bouncing off the bat, so it ends up going faster when it comes back. And we want to figure out the maximum force given that the contact time is 0.6 milliseconds. So we just proceed through this. So this is the sort of thing we can write down. We've got a before picture and an after picture. And before, in this case, the way this has been drawn, the velocity is negative 20 meters per second. After, it's positive 40 meters per second. And so we can work out the change in momentum. It's the final velocity times m, and the final velocity is positive. So this time it's positive, unlike this example where it was negative. And when we have the positive quantity minus the initial momentum had two negatives, has a negative sign, and since we're subtracting it, those two negative signs cancel out. So it's a change in momentum, 9 kilogram meters per second, and then we can work out the average, the impulse from that. And since the time is this very small amount of time, 3 times 10 to the minus 4 seconds, 0.3 milliseconds, when we divide that impulse by that small time, we get a very, very large force. So remember that this top line is equal to 3 times 10 to the minus 4, a very small number, times this big number, 30,000 newtons. So when you hit hit something, a cricket bat or a baseball bat, it makes a lot of noise, and it actually exerts a lot of force for a short time. Now, so far we've been talking quite a lot about, what's the actual force that's happening here. But in many cases, we don't really care, do we? All we're really interested in is how fast the ball is going before it hits the table, and how fast it's going after it hits the table. In many cases, the details of what exactly happened when it bounced aren't really important to us. So often all we're interested in is the initial momentum and the final momentum. Okay, so here's a little numerical example. So this example is very similar to these examples we've just been doing, so I hope it's not too hard. So we've got this cart. This cart, it's traveling at 2 meters per second in the negative x direction, and it weighs 10 kilograms. And then it bounces off the wall, and now it's going at 1 meter per second in the positive x direction. So this is pretty similar to the two things we've just done. So what do people think is the answer? E3, okay. Anyone else have any ideas? Okay, so we're mostly getting 30 here. That looks sort of reasonable, doesn't it? Here's the working. So the change in momentum this is the final momentum. 1 times 10 is 10 kilogram meters per second. So it's the final momentum minus the initial momentum, which was negative 2 times 10 is 20. And so 10 minus negative 20 is 10 plus 20, which is 30 kilogram meters per second. There's a few more problems here which we could talk a little bit about. This one's not too hard. So this is a rocket sled with a rocket. My drawing is pretty useless. So it was, what do we have? Mass is 500 kilograms. The x, for example, is 20 meters per second. So that's x direction. So that's our before. And then afterwards, after you turn on the rocket for a while, now what are we asking? What's the final? Vx final equals what? Vx initial is this. And we've applied 5 seconds, so the J was 1,000 newtons times 5 seconds. That was the impulse, or the change in momentum. So the delta P is m m times delta v. So we can work out from here that the 5,000 is m delta v, so delta v is going to be 5,000 divided by m, which was 500, which is 10 meters per second. So that was delta v, that's vf minus vi. So the initial velocity was 20, so the final velocity 10 meters per second, so the vf is going to be 10 meters per second plus, taking over the other side, plus 20 meters per second equals 30 meters per second. So you might, I'm not sure if this is terribly clear, but it might be starting to become clear that the way we're doing this, these calculations are relatively easy. If we were doing them before we started introducing these ideas of momentum and impulse, we might have used those kinematic equations and wrote down a whole lot of equations and fiddled around with them. This is a very straightforward way of doing the calculation. Of course, we could have just gone back and done that. Now this is a more complicated problem, and I'm not sure if I've really got time to do justice to the whole problem. But this is related to the reason why you should be like a hedgehog. The way it's written is a little bit strange. I think what it's saying is what would be the difference? What would be the difference if you run your car into a concrete barrier and you stop really suddenly? So that's part B, where there's the crumple zone of the car, which is about 1 meter. So you're getting rid of all that momentum and velocity. All that velocity is the acceleration has to happen in that very, very short distance, that 1 meter distance. Alternatively, you have a whole lot of water barrels, and the car goes bang, 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 bang into the barrels, and so it's slowing down over the distance of 20 meters instead of over the distance of just 1 meter. So what do we know about this? We've got V is 20 meters per second. So that's like VI is 20 meters per second. VF is equal to 0. Okay. And actually, if we're going to estimate the force on the driver, we need some information that's not there, right? Because the force is mass times acceleration. So if we're going to finish this problem, we'd have to assume mass of driver equals, I don't know, let's say 50 kilograms, because that's a nice round number. So what we're going to need to do to figure out here is what's the acceleration. Or No, I think we can do better than that, actually. Okay. Right. So I think I was actually thinking it out a little bit too difficult a way. So let's think about, you know, this looks like it's quite a difficult problem, right? If we use the sort of thing we've been doing in the last week or two, we would write down those kinematic equations or something. We'd start writing down things like VF is VI plus A delta T, and XF is XI plus VI delta T plus half A delta T squared. And that's really annoying. That's quite hard. Right? But so can we do this? Can we do this better by looking at the by using momentum? So I hadn't really thought that out very well. So let's see how we could do that. So the change in momentum, you can work out the change in momentum on the passenger in the car. That's going to be the change in velocity multiplied by m, or 20 meters per second times, what did we say, 50 kilograms. So that's 1,000 kilograms meters per 1,000 kilograms meters per second. Now I think unfortunately we're still going to so that change in momentum is equal to the impulse, which is equal to the force times the time. So in order to work this out, work out the force, we're going to need the force is going to be 1,000 kilograms meters per second divided by the time. So what we're going to need to do is work out what that time is, and I don't think there's much substitute for just doing it. I think from this equation here, sorry, I'm getting a little low on time here, I can write down that the acceleration from looking at those, I can write down the acceleration as v squared over 2 delta x, and time is v over a, and so I get the time being 2 dividing v by v squared 2 delta x, that goes to the top, then 2 delta x v squared sorry. If I take this, 1 over a is 2 delta x over v squared, and the v is v, so I can cancel that out. So the time is 2 delta x divided by v. So I can work out, I'm not going to put the numbers in because I'll probably get them wrong right now, but we can work out, if we work out the time, the delta t, we're going to be able to substitute that into there. And since the delta t is proportional to how long a distance it takes us to stop, then obviously you're going to have a lot less force if you're running into the barrels than if you're running into the brick wall. Okay, so I think I'd better stop there. So, so far we've talked about essentially forces acting on a particular object, like the ball bouncing or being hit. And next time we'll talk about what happens to momentum when we have two objects. Hi. Did I? Oh, did I write it? Ah. Ah.
With the rocket, you just, 5,000 thrust.
Oh, well, that was to get the.
I might have missed.
I might have written. Well,
seen it, but
I sometimes write the wrong thing or say the wrong thing or something.
just stuck in my mind.
Oh, yeah, it's good to. Where was it? Down here, was it the?
No, I think it might have been a bit further.
This one before, after this is the rocket. Was that the rocket? Oh no, this one.
Yeah, so 1,000 newtons. So
Well, this is J. It was that's the impulse. It was 1,000 newtons times. So the impulse was 1,000 newtons
okay.
times so many seconds.
So
Whereas the
impulse is force times time, is it?
yeah, the impulse is force times time, whereas the momentum is mass times velocity.
Okay, cool. That must be where I've gone.
Yeah.
Awesome, thank you.
Oh, that's good. Well, it's good to check that. Hello. All right. How are you getting on?
Oh, slowly but surely getting better.
Oh, is it getting better?
It is getting better, but it's not good enough. But it is getting better.
Oh, okay. Did you have a particular question? Or?
I do, yes. So we were talking about circular motion.
Oh, yeah.
Um,
Should have got everything, haven't I? It's always best to leave the